Welcome to Study Loop.
So you can shoot an arrow straight up so that it reaches the top of a 25-meter tall building. The first part of the question is, how far will the arrow travel if you shoot it horizontally while pulling the bow in the same way? And this is the idea that we release the bow and get rid of the arrow at the same velocity. So we start with the idea of shooting an arrow straight up with the same velocity to see essentially what that velocity is. So we'll start with essentially a bit of prep work for this question. So we'll take a vertical that is wholly y direction, if we define x and y to be horizontal and vertical like this, and we take an entirely vertical view of this situation. So we have S, U, V, A, and T. I do like doing it this way. It gives us some general kinematics terms that we can use. So the distance that our arrow has to travel is 25 meters, starting at some unknown velocity, which we'll just mark as u. And if it can reach the top, we'll assume that it reaches the top exactly when the arrow has slowed to a stop. Vertically, the acceleration is obviously negative g, g being 9.8, and t is irrelevant. And so we use our kinematics equation, v squared is equal to u squared plus 2as. So this gives us 0 is equal to u squared minus 2 times 25 is 50. So we've got 50g. And this is all nice. So the next thing we're going to do is we're going to take 50g over to the other side. And this is equal to u squared. And so finally 50g square rooted is equal to the launch velocity of our arrow. And it's time to put this into a calculator. It's a fairly straightforward step, and we find that the answer is 22.1 meters per second. Okay, so now onto the proper question. Now we've found that velocity. The first part asks us to how far will the arrow travel if you shoot it horizontally, pulling the bow in the same way, so same launch velocity. And the arrow starts 1.45 meters above the ground. And so once again, we don't need to consider anything horizontal because the arrow isn't really being slowed down too much immediately. We need to know how long the time flight is, and then we can plug this into a simple horizontal equation afterwards. So we'll once again work in the y direction and use S, U, V, A, and T for our next kinematics equation. So we're descending 1.45 meters with an initial velocity vertically of 0. Our final velocity doesn't matter, and we're descending at an acceleration of negative g, and if we're incorporating the negative here, we should incorporate it here as well. We're going down 1.45 meters, and our acceleration is negative 9.8 meters per second squared. And of course, the time is something that we don't know. So we write out our kinematics equation. S is equal to ut plus half of at squared. And the first thing we note here is that ut is 0 because our initial velocity is 0 vertically. So that leaves us with negative 1.45. Let's make that negative a little clearer. Is equal to negative g over 2 t squared. And we cancel our negatives, leaving us with 1.45 doubled is 2.9 divided by g, which is 9.8, is t squared. And so in our calculator, we now want to place t being equal to the square root of 2.9 over 9.8. And what value do we get? Quickly placing in the calculator, we find out that the value for our t is 0.54. This is how long the arrow takes to descend. And so for how far do we go? Well, now we consider the x direction. Well, we have fired and we get a distance of, our distance is equal to our velocity multiplied by time, because there's no acceleration in the x direction, there's no air resistance or anything like that. And hence the distance that we go is just equal to our velocity 22.1 multiplied by 0.54. And our answer is, should we stick some seconds here just so we've got some units? And so our answer at this point, we just put into a calculator and find our answer is 11.9 meters. Okay, the question now goes on to ask, where do you need to put the target that is, put a target that is 1.45 meters above the ground in order to hit it if you aim 30 degrees above the horizontal? So it's a similar sort of question, except this time we are aiming with some angle of 30 degrees and we're hitting a target in the distance. And this time we need to go slightly more two-dimensional to get all of our distances, and of course we need to know where to put the target, which is basically a question of how far it goes. So the question is therefore, what do we have in both directions? So we'll just write all of our unknowns and knowns in the two directions, and we're going to once again get S, U, V, A, and T. So S in the x direction, how far are we going to go? Well, that's definitely an unknown, and that's what we want to figure out. In the horizontal direction, our velocity is, if we remember back up here, 22.1. But of course it's 22.1 cosine of 30. And if there's no air resistance, our final velocity is the same, because there's no acceleration in this direction. So you see the problems actually have a similar form. No acceleration in the x direction, and our time is also an unknown. So the distance we go in y, well, if we are firing from 1.45 meters up and it is descending back to that height, we have a displacement of 0. So it's either gone no distance or a full distance. Next, our initial velocity is of course 22.1 sine of 30. And due to symmetry arguments, we can also say that our final velocity is 22.1 sine of 30, but negative. And this will help us in order to figure this out a little bit more. Naturally, we descend at 9.8 meters per second squared as an acceleration, and it's negative because we are descending. And time, once again, is an unknown. And the reason we can make this argument that our final velocity is simply going to be the negative of our initial velocity is because this is going to follow a parabolic path, which is symmetrical. If we fall to the same height, whatever height you are going up at, you are coming down at if there's no air resistance. Okay, so now we move on and try and solve some of these equations. Well, the first thing we want to do is we want to figure out how long we've been in the air for, and we can get this from the vertical direction. So how long have we been in the air for? Well, what values do we have? We have V, we have U, we have A, so we might as well use V equals U plus AT. So substituting, we have negative 22.1 sine 30 is equal to 22.1 sine 30, and then minus GT, and we can rearrange for G. The next thing to notice is we can take the negative 22.1 sine 30 from the left hand side, move it to the right, and the negative GT from the right and move it to the left. So we actually get 2 multiplied by 22.1 sine 30. And that is equal to gt, but if we just write t on this side, it would be gt, but of course we can take the g from this side and divide the second side by that. And another thing to note is that sine 30 is a half, which will cancel with this 2 out the front. So actually, we just have 22.1 divided by 9.8. And the answer there is simply 2.26 seconds. Okay, we're very close to solving now, because the next thing that we have to do is figure out how long our flight is. So we now go in the horizontal direction. We substitute this time, and we say that our distance horizontally is simply going to be equal to our velocity horizontally multiplied by the time it takes. And so that is 22.1 cosine of 30 multiplied by 2.26. Now we put this into a calculator and find the answer is 43.3 meters. And this is how far the target needs to be away. So this is great. Okay, and the final part, determine the maximum distance that you can move the target and hit it with an arrow. So essentially, we have made a couple of assumptions here, that the air resistance is negligible and that the arrow, when it's fired at the same velocity in all three cases, and you have to assume that that's the case. You will fire the arrow at the same height as the target in the final case. So these are all the assumptions, which means that actually this is already the maximum distance that you can leave it away from the target and still hit it with the arrow. It depends how big the target is if we need to do any more calculations on this front. For example, if we definitely knew that the target had a width about it, we could then have an additional time of flight where if the center of the target was at our radius, we could do some more calculations. For example, if we said then that the target was going to, in our flight, just a quick hypothetical, descend a further y meters, and our velocity is currently at negative 22.1 sine theta, which is what we assumed it to be as it was descending. Further velocities don't really matter, and a is still negative g, and the time taken is also kind of unimportant. We can relate a few of these things so that we can rearrange for the time taken. So no, in fact the time taken is quite important. So the further distance y is simply the radius that we've marked of our target, and therefore an equation with s, u, a and t is going to give us the following, that y is equal to negative 22.1 sine 30 multiplied by t, and then add to that we take off negative g over 2 t squared. And this is a quadratic. We can also remember that the sine 30 is sine 30 would just be substituted as over 2, which would simplify our equation a little bit. And we could go even further. We could say that 2y is equal to minus 22.1 t minus g over, minus g t squared. So we're getting this into an easy quadratic version. Now 2y is equal to the diameter of the target, so we'll replace that with a d. And that actually leaves us with a very simple quadratic of gt squared plus 22.1 t plus the diameter of the target is equal to 0 as our quadratic, and hence we have negative 22.1. We could also call this our initial velocity, plus minus the square root of 22.1 squared minus 4 multiplied by g multiplied by the diameter of the target, and all of this over 2g. And this is now our time of flight. And let's be sensible in what's going on here, that we can't have a negative time, and hence the negative version isn't going to work here. So we just want the positive version in this equation, so we don't need to consider both the plus and minus. And finally, the distance that we travel, additional distance that we travel, is going to be equal to u multiplied by t. So this is simply equal to 22.1 cosine of 30 multiplied by negative 22.1 plus the square root of 22.1 minus 4 g d all over 2g. And then we're essentially trying to make an additional assumption for the distance that we travel. So I'm just going to sense check this answer to see if everything makes sense at this point, and see if we have anything that is a bit unusual. So it's worth just having a look here at this equation that we've written. So we were going down at this velocity, and therefore we are descending certain values downwards. Oh, of course, no, there is a slight mistake, that this should be negative and this should be negative, and hence, therefore, this should be negative, and in the square root, that should be positive. It's always good to sense check your answers. Sometimes you do run a little short, and something did look a bit unusual here. The time was looking to always be negative. So anyway, this is our additional distance, and it's not very nice, but it is, in theory, the maximum extra distance we could get if we were aiming for the center of the target and it had a radius associated with it. So finally, max distance obviously is variable. It's dependent on the size of your target. But simply put, the max distance you can get is your 43.3 meters that you already had, in addition to a formula which is 22.1 cosine of 30. And we can even neaten up this part in the square, in the brackets as well, in that we have the square root of 22.1 plus 4 g d, where d is the diameter of the target. Then we subtract from that 22.1 and divide the whole thing by 2g. And this is the maximum possible distance if you still want to hit the target, but maybe not get a bullseye. So it's a bit lengthy, but it's a good play with algebra here. And then